Hello, this is a tutorial on molecular geometry from molecule type. So I'm going to teach you how to recognize from your Lewis dot structure what type of molecule you have, and then that translates directly into a very specific type of geometry with known bond angles. So the very first thing you're going to do is you're going to use your Lewis dot structure. So if you don't know how to draw your Lewis dot structures, go back and get the tutorial on that. First, I want you to focus on the central atom. That's what we're going to designate with the letter A. And then I want to know how many atoms are actually bonded to the central atom. That will be designated with a B. And then the third thing I want to know is how many lone pair of electrons are on the central atom. That will be designated with the letter E for electron pair. So let's take a look at some of our types and illustrations. So what I want to do is I want to give some examples of these. The first example I have for an AB molecule is hydrochloric acid. So we would have HCl. We have 1 valence electron for the hydrogen, 7 for chlorine, which would give me a total of 8. And so I have 8 dots to draw. So chlorine will be my central atom because hydrogen never is. I put my hydrogen in. So see how I have AB? Notice I don't put E3 because it really doesn't matter. There's only 2 atoms. And anytime you only have 2 atoms, it's got to be a linear situation, just like 2 points determine a line. Another example that might come up would be if you have more than 2 atoms, like this one, C2H2. And so you have 4 electrons for each carbon and 1 electron for each hydrogen, so 8 plus 2. I get to draw a total of 10 dots. So we know with carbon they will always bond together, and so this is actually going to require a double bond. Again, if you're not sure how to develop the Lewis dot structure for this, then you need to, actually this will be a triple bond, sorry. You need to take a look at that. That will also be a linear situation, and that might fit down into the AB2 one a little bit better. Another example of the AB2 one would be carbon dioxide. This is what the structure for carbon dioxide looks like. It's a multiple bond, a double bond to oxygen. So you see everything has 8 electrons when you do that. And there's no unshared pair on the central atom. That's what makes it linear at 180 degrees. Another example of that type is one that is a metal with a nonmetal. For example, BeI2 would be an example. So I draw 2 for the B and 7 for each iodine. That gives me 16 dots to draw. When we are drawing with metals, metals do not have to have an octet, but the nonmetals do. So iodine is octetted, and there's no unshared pair on the beryllium. So this also is a linear atom fitting the AB2 with no unshared electron pair there. The next one we're going to look at, we're going to start building the tetrahedral family. The tetrahedral family, there's either 4 things bonded or 4 things arranged around it. Sometimes things aren't bonded but are unshared pair on the central atom. So let's start off with methane. Methane looks like this as a Lewis dot structure. So we have central atom A, B4, no unshared pair. So AB4 is our molecule type. That translates into tetrahedral. That means every bond angle in here will be 109.5 for the VSEPR theory to hold up, that the valence shells are repelling themselves as far apart as possible. The next one we have is pyramidal. An example of a pyramidal molecule is ammonia. So we have, again, 4 things around ammonia, but only 3 things are bonded. The 4th thing is an unshared pair. So we have AB3E, which is pyramidal. The bond angle here is really about 107. it'll be much less. The reason is this lone pair actually pushes these a little bit further than if it had a nucleus to it with a positive charge up there. And so that's why that's a little bit less than 109.5 for the bond angle. And so that lone pair is what causes that to happen. So let's continue building from our molecule types to, so we go to AB2E2, 109 bent. The example of that is water. Oxygen is the central atom. There are 2 hydrogens bonded and 2 lone pairs. So that's how we get A, B2, E2 for the central atom. And so that's what we get for a bent molecule. Let's try a trigonal planar. An example of that would be this molecule. This is actually formaldehyde. It's a double bond to oxygen. Remember that single bonds and double bonds don't count separately. So we have a single bond to hydrogen, single bond, double bond, but I still have no unshared pair. So I have 3 things bonded, no unshared pair. That's what gives me the AB3, trigonal planar, bond angle is 120. It's called planar because it's flat. It lies within a single plane. And so that's where we get the trigonal planar idea from. Let's take a look at AB2E for the next one. That would be like tin 2 chloride. Remember, tin is a metal, so it doesn't have to have an octet. Chlorine cannot have multiple bonds, so we can't result in double bonding to give chlorine an octet, or I mean tin an octet. Chlorine will have one. So there's 4 plus 2 times 7, 14. I get to draw 18 dots. I've drawn 16, so there's an extra 2 that I will tack onto the central atom. So I have A, B2, and my lone pair E. So I have 120 bent. And again, this lone pair actually pushes it so it makes it less than 120. The last 2 I have are what we refer to as the expanded valences. The expanded valence means that you're going to have more than 8 electrons on the central atom. So an example of the expanded valence of trigonal bipyramidal would be PCl5. So we put phosphorus, there's 5 plus 5 times 7. I get to draw 40 dots. For these, I like to draw lines to represent the shared pair. So 1, 2, 3, 4, 5. I've drawn 10 electrons so far. I'm going to octet each of my chlorines by putting 6 dots around it, because this represents 2. And here we have PCl5. PCl5 is going to arrange itself that it's going to have that trigonal planar in the middle, so that's 120. This is 90. You could say 90 and 180 because these are 180 apart. This is 90. So you could include an and a 180 here if you wanted to. That's fine too, because there is a linear component here. Octahedrals are our last example. Again, it's another expanded valence, more than 8 electrons around the central atom. Sulfur is a very common one that does that. Let's take a look at sulfur hexachloride. Again, I prefer to draw lines. And then I will octet each of my chlorines. And that will give me the 48 dots I'm allowed to draw. And so I have AB6, which is octahedral, and all of these are 90 degrees. If you also wanted to put 180 here, you could, because this is 180, this is 180, this is 180. So you've got that bond angle going in there too. Well, I hope you found this helpful. If you need to watch it again, watch it again.